So, welcome everyone. I don't have that slides in here, so I'll just leave it here and look that way. So, if you want any question, just shout. So this is, that was an internal presentation that we had during the sprint, and we thought it would be a good idea to expand this to Connect. So the idea is to give toolchain people an idea of the differences between LLVM, GCC, and to walk through the LLVM middle end, back end to understand how everything works. So, of course, LLVM is just a bunch of things. It's not one. It's not even a toolchain. It's just a bunch of libraries that we happen to use as a toolchain, but it has lots of tools, libraries, and different backends and front ends, etc. So, just to make a comparison with the GNU toolchain, the front end, so we have Clang, but we also have Flang and other front ends, but the default one for C++, which is what most of us care. So the GNU has the GCC and then CC1 and etc. Middle end, LLVM, middle end and back end, they're all in the same project, and GCC as well, so that's good. The assembler, we don't have an assembler per se. We have an assembler library, and we don't try to use this, so we don't try to output assembly and then run an assembler. We always output either assembly or object directly. So what's equivalent to gas in GNU, we don't have the equivalent in LLVM. You can try to use LLVM-MC, but that's not a tool, it's just a testing thing. But the best thing to do is to use the front end, Clang, to interpret the assembly, so it does just like GCC reads assembly files and pass it directly to the assembler. We just read the assembly files and use the assembly library. So the linker, we have LLD. It's almost working for ARCC4 and halfway through for ARM. So the libraries, the GNU has the runtime libraries, libgcc, and the C++ libraries. That in LLVM we have similar, so compiler RT and libc++, but we don't have a C library. And we don't have a C library because it's really hard to write C libraries, and there are enough of them in the world. We don't need another one, another broken one. So, and people use all C libraries with LLVM, Muscle, newlib, glibc, and it works, so there's no point in trying to get a new one. Debugger, same thing, GDB and GDB server. We have LLDB and LLDB server, and it seems to be working good for ARM and ARCC4. So one of the first things that people get confused when they start using Clang or LLVM is that GCC is like one big block of things that you just say GCC this, and it just does what it has to do. But when you go to Clang and LLVM, there are so many tools and so many people using the tools in. So if you see on the right side, this is an idea of some of the tools, some of the most visible tools that people use. And it really gets messy. But you can also do the direct route as you do in GCC. And if it finds the right tools, if you can convince Clang to find the right tools, then you get an executable in the end. But you can, so the easiest way to use is to use Clang into an object file and then try to use a linker with the libraries, etc. The problem there is only that you may have trouble finding headers, but it's a simpler path. If you try to go direct, you have to pass, if it's like cross-compiling or something, you might have to pass linker flags, and then it's not going to find the right linker. And so, but then again, if you go to the individual steps, the outcome, the executable that comes in the end may be different, because everything in there is a library. the way Clang uses the libraries may be different than the way that each one of the individual steps use the same libraries. Because the libraries are configured at runtime, so you pass all the parameters, and the parameters are not the same depending on which tool you use. We are trying to get into a world where they're all the same, but because some of these tools, especially opt and LLC, they are developer tools you're not supposed to be using anyway, so people don't feel compelled to have the exact same syntax and the same parameters. So, well, yeah, that's what I just said. Not all paths are created equal, means that they're used different, and then the default path structure can also be different, so opt may have a different order than Clang, and because when you call up the path manager, you can tell which passes you want, and they can pass different passes, or if you add flags, they can put those flags in a different order, and then you come up with a different result. Not all tools can pass all the arguments, so the Clang driver can handle some linker and assembly flags, but not all of them. So if you just produce an assembly and then run, I don't know, the GNU assembler with the flags that you want, it works. If you try to pass via -WA, it won't. And so these things, what we do is, what we've been doing for the past few years is, whatever people need, we just implement, but we're not going to go into a full GNU compatibility mode to make sure that we pass everything that is possible, because that would then mean that we're going to have to support all those different configurations that the GNU does, and the GNU guys don't like supporting all these old style that people do, and so we have the benefit of not having to. The other problem we have is that when GCC is compiled, you can pass the -- with this and that hard codes the toolchain into understanding its own library path, understanding its own headers, its own tools and everything, and its own triples and platform choices. And so, for instance, when Debian calls its triple ARM Linux GNU ABI HF, that means something. When Ubuntu calls the same triple, it means something completely different. And for LLVM, when we say a triple, we only have one default. We can't have multiple defaults. And then people have to use like MCPU, MFPU, MABI, float ABI, or whatever to make sure that it behaves in the same way. And I think, I may be wrong, but I think that not all with flags are transparent in the triple or compiler flags. So you could have some of those options affecting the code chain, but not being able to set via flags. So like CPU, FPU, float ABI, those things you can change with the flags, but there may be some options that are not accessible via flags that just behave differently. I can't think of any now, but if there is at least one, we are already in bad shape. And then, well, of course, different order produces different results. If you try to opt 0, then opt 2, you're going to get a different result, but that is the same as GCC, because it's just how compilers work. But in LLVM, this extends to, if you emit assembly and then use Clang itself to reassemble and produce code, you may have a different result than if you produce object files directly. And that's not a problem for GNU, because in GCC, it always outputs assembly, always uses the assembler. So the order is guaranteed to be the same. Even if you only invoke one tool, that one tool is going to invoke the other tools on its own. But because LLVM uses them as libraries, the end result might be different. So you have to be careful with the kinds of permutations that you try to use, and you have to be aware that they may produce different results, maybe not broken, but different results. So don't expect distributive, associative, or commutative behavior in any of those things. So this is an example of a C to IR transformation. So on the side you have a C code. On the center and right, you have the x86 and ARM IR. And so one of the big things that new people come to LLVM, they say, oh, I produced IR, so why can't I compile this to Intel and ARM and MIPS and whatever, is because the IR is not target independent. It's not meant to be a target independent language. C is a target independent-ish language if you make it portable, but IR you can't make it portable because when the front end lowers, for instance, structures, it lowers then in target ABI dependent. So the x86 ABI may be different than the ARM ABI, and then all bets are off. So in this case here, well, obviously the I64 type is the default on x86 64, and I32, which is integer 32, is the default on ARM. But other things like on the ARM side, you have the this is the procedure call standard, which is saying here this is AA PCS CC, and which of course means nothing on Intel. And on the other side, you don't have any calling convention, but it just assumes the default. And on ARM, you can't just assume the default. You have to actually specify, because people do mix them more often than on Intel. And the other thing you have here is the unwind table, for instance. That is the default to always emit the unwind table on every function on Intel, when we don't do this on ARM because it wastes, it increases the code size. So we only do this if you actually ask for unwind tables, or if you ask for exceptions or debug or something. So yeah, I think that's it. Did anyone notice the undefined behavior in there? Oh, you can't see probably. Ignore them. In the sprints, the screen was closer to us, so it was easier. So this is more ABI differences. Well, the first thing you notice is the target triple on the top, which if it's ARM, it says ARM v7, Linux, whatever. If it's x86, unknown, Linux, GNU. And that gives you the hint for which platform the IR was generated to. And so in this case, for instance, if I get the ARM one, and I try to say, you know what, I'm going to change all the R64 for I32, and let's hope it sticks, it wouldn't work, because, for instance, on ARM, char is unsigned by default, and on x86, it's signed by default. And then, you know, you have completely different undefined behavior on type expansions and shifts and operations and stuff. And the other funny thing is, on Intel, a constructor returns void, because the constructor has a pointer already to the object. It constructs the object and goes off. Well, on ARM, the constructors, the ABI, the C++ ABI of ARM says that the constructor should return a pointer to the object you just constructed, so you can chain constructors. And then now, if you try to run, so that is returning the object, he is returning void. If you try to use one on the other, you know, the ABI is going to be completely broken. So another thing, don't expect IR to work in any other thing other than the one it was generated to. And even if it's ARM, you know, you say ARM v7, but you say, oh, you know, I'm trying to just change this to make it work on ARM v8 or ARM v6, it's not going to work. You have to recompile. Right, so this is a bit more in the internals of the compiler. Once you have the IR, you then run through a series of optimization passes. And there are basically two types of passes. One of them is like an analysis, and instead of changing the IR, they just generate data. And the data can be in the shape of metadata, or it can be some structures inside the compiler. And that would then just lay out some information for the transformation passes to use. So if you have some, for instance, the loop vectorization needs some alias analysis, and then, well, you say the loop vectorizer has a dependency on these analysis passes, and then every time you ask the loop vectorizer to run, those analysis passes will be executed before, and then the data structures will be filled and the metadata will be set so the vectorizer can work well. And well, the scope, you can have all the way from a basic block specific pass to module level passes and anything in between. The loop pass is an interesting one because you can have a region which is like a number of basic blocks, but a loop has to have a specific shape. So it has to have like a main body, the latch, and the top one. So if it doesn't have that shape, then the loop passes will not work. So the way to register this is you have a static registration with initialize the pass, and then you have a few functions that says what do I depend on and what assumptions do I break. So this is one of the interesting things on the passes for LLVM, is that you can say what kind of analysis passes you break after you finish. So if you have two transformation passes that need the same 5 analysis passes, but the first one only breaks 2 of those analysis passes, then you don't need to run the other 3. For the second pass, you just run the 2 that the first one broke, because you assume that the other 3 are still intact. So that kind of optimizes the way on how many analysis passes you run in the compiler. Right. Oh yeah, so the transformation ones, what you do, you normally, if it's like a basic block pass, you open the basic block, you iterate through the instructions, and you see if you want to change or not. If you do want to change, then you create a new basic block and you do the change that you want, and then you replace the basic blocks and delete the old one. But most of the passes, I don't know if all of them, they do a validate on the IR before. So if they do something stupid and the validate doesn't like it, they just give up and pretend nothing happened. So this is an example of a transformation. You can use opt to test optimization passes or to debug if you're developing one. So this is one example. I was trying to get an example of optimization pass and how to see the lines changing, but then so SROA is a scalar replacement of aggregates, which is a way of like dissolving the structure and only using the internal elements as separate variables. And it gives you better locality, or so it's an interesting optimization. But the first IR on the right, on the left, is like 0, so it has all the CRUD that the front end generates that is not really interesting. And then I just passed this SROA thing, and I got like, as I would expect, because that was like a div, right? You divide one by the other number, and after SROA, I get the perfect IR, and I say, you know what, that doesn't make sense, because there are no aggregates, there are no, there's no access to anything. It's just 2 variables on the stack or on the argument. And so how do you see what's going on? One way is you use the print before and after, and then as you pass opt, the optimization levels on the IR, it will print the IR as it was before and after each one of the optimization passes. So I was expecting that some of the previous passes, if SROA depended on some of the transformation passes, that transformation pass would be the one that was optimizing the way I want. But it wasn't. So the IR was perfect, it was like full, all the way to the SROA, and then suddenly it wasn't anymore. And I said, okay, there's something wrong with this pass. And then when you look at the code, you see that the code then needs to perform some promotions, because, and that's not, it's not exactly the same thing it was on the previous slide, because the previous slide was saying you have this analysis and you have this transformation. This actually depends on the transformation. And that transformation then, the perform promotion, does promote mem to reg variables. So all the stack allocation on the left, it's irrelevant. And then when you try to promote them to registers, they realize, you know what, they're already in registers, R0 and R1, so I can throw all this away. So it's, this is an interesting way to show that the tools are there and they help you in the general case, but sometimes you have to dig into the code and see what's going on. And that had nothing to do with throw at all, but it's an interesting example. So after you do all the optimizations, you need to lower this into machine code. And right now, the selection, the instruction selection that we use is the selection DAG. Is going to be replaced, hopefully, in the next year or so. But and the way it works, it's very simple, very naive. This one, I haven't looked at the global OSL yet, but this one is very naive. You just have like basic blocks, and you have IR instructions, and then there is like a target independent lowering. And the target independent lowering says, oh, this is an add. I'll lower this as an add DAG node. But add doesn't mean anything in any architecture. You have different add instructions, different constraints, different addressing modes, etc. So the generic one is just going to pass as if the target is this generic thing that we think exists. And then you're going to have a target-specific pass that is going to then look at all these nodes and say, do I have this? Is this legal in my architecture? If not, then it tries to promote the type or to do some other modifications, split instructions, join instructions. So the cycle is there. So for each instruction, you selection DAG builder visit, which is the one that gets this generic thing. And then the other one, when you do the code gen and emit DAG, is the one that is going to get the target-specific ones. And then you try to legalize types or combine instructions. And then at the end, it does the instruction selection and then run the scheduler. So again, I apologize. This was meant for a closer audience. But so one of the examples is, as you lower to this generic DAG, this instruction here is an add, 64-bit. And here you already have register names, specific register names, like R1 and R0. And so it's a mix of target specific with target agnostic, because the ABI gets in first. Because if the register allocator gets before the ABI sets in, then it's going to start using R1, R0, and then it's going to have to spill to use the arguments in the function. So you just fix everything that you have to fix first, and then you pass. So when it legalized the types, well, ARM doesn't have a 64-bit legal type. So what it does, and this is still not ARM specific, it's 32-bit specific, and then it splits into adds. So you have add top, add bottom, and then you have the copy from reg, copy to reg, to make sure that the adds, that now the types are legal, and now they're R32, okay, it's legal on ARM, let's continue. And then after you do, when you do the legalize is like, is this legal in the target, not just with this type size? And then it starts, so here, the instruction name here is add, very generic. The instruction here is like add E and add C, still generic. And here you get to the ARM specific. So this is ARM ISD add E, ARM ISD add C. And then you're getting closer to the type, the target specific instruction with the constraints and everything. So I don't know if you guys are interested in a bit of the selection DAG structure, but the red bits are glue, which means don't move these things apart. If you move the up and down, keep them in blocks. The chain, which is the blue one, is like program order, so you know how it was in the source code. So you can scramble the DAG as much as you want, but the chain is going to tell you how it was, which order it was in the source code. Right, legalized types. So yeah, this is the basic silly type legalizing, that it just goes to each one of the instructions and see if the type is legal. And if the type is not legal, then it tries to expand the integer or promote a float or scalarize a vector. And each one of these things is an action. depending on which type it is, it just does the action on it and then goes back again. So this part of the code is really ugly because it's a huge switch with lots of go-tos in between. So it's something, if you want to contribute to LLVM, don't start here. It's disgusting. But this is all going away, hopefully, quick enough. So the DAG combine, it's what it is. It just combines nodes. And so sometimes when you have like a split, so if the types are not legal, then it starts splitting things. And if it splits too much, or if there are two instructions that actually have one, so the obvious example, it doesn't work at this level, but an obvious example would be something like multiply and add. You just fuse them together, but it's not at this level. That is at a different level. So this, oh yeah, and you implement the methods combine and then the opcode, which means this is the way to pattern match things. So it just, if there is an implementation, it just runs it and combines stuff. And then cycles back again until it's valid. So so after the types are at least sane, it starts doing the legalization to get the target specific behavior. And so like if it's legal, you continue, and if it's not, you try to promote it, and then this is a bit silly as well. It tries to promote to the largest type possible in the target. So in ARM it will be 32, and if there are no instructions on 32 bits on that, it just shifts back. So tries to like reduce the size to 16, 8, etc. Expand then. These are so these rules, they are not like one after the other. Is you register them. You say this instruction can be lowered via promotion or via expansion or custom. And so these things are like increased cost of compile time. So promote is quick, and you do this if the compiler can already understand it just via promotion. Expand, then you need some table gen magic. Table gen is, I think we have a slide on this, is the target description files. Custom is then, now this is like full-blown C++ code that then gets the nodes and inspect them and break them apart and build them again, replace the instruction. So this is the most, like the most expensive for compile time. And if you really have no idea how to do this, you transform into a library call, and if you can, transform into a library call and just hope for the best. So the instruction selection as which then it runs after that. It's the part that gets the generic instructions into ARM-specific instructions. And it just does some type legalization, an ABI register, etc. It's trying to get everything into an ARM-specific DAG. And inline, oh yes, this is one thing that confused people. When you have inline assembly in your C code, it's lowered into IR as a text, and with some fields for the constraints. And in the DAG, it's still text. And in here, it's still text. So this is only going to be used later on when you actually transform from a DAG to a machine code representation. Because different from GCC, in GCC, if you say inline ASM something, GCC completely ignores whatever's in there. Even if it's invalid, it doesn't care. It just outputs that into the assembly file and Bob's your uncle. But Clang or LLVM, it doesn't do that. It reads after, at the lower level, when it has access to the instructions and the parser, it reads that and it expects that to be valid assembly. And it has to match all the registers, and it has to match all the addressing modes and everything. And funny enough, it doesn't have to connect to the rest of the code, but it has to be valid assembly. So you can try to output some extra directives in there, and it works because it's valid assembly. But there's no guarantee that whatever you fiddle in there is not using registers that are already being used by other sides if you don't specify the right constraints. So I don't know how far does it go to, because it's a disconnected thing. One of them is the register allocator, choosing registers. So I don't think do you know if when it parses the inline assembly, it does register spilling if it tries to use the wrong register? Okay, yeah, I think that would be too much. Yeah, anyway.
I think once you got to the MC layer, it's all done.
It is, but then if the user specify a register by name, and that register is already being used by the register allocator and not spilled, do you just whatever?
That sounds.
Well, you can have the constraints, but you can also write registers. Anyway, so then it goes to the scheduler, which does sorts the DAG in topological order and keeps the groups together, so you know by the glue thing, so you know how to move them apart, around, but not apart. Yeah, there you go. The glue keeps them paired, and the target schedule is in the table gen, so you can learn on the. You can read the schedule. It's not really too complicated. It's and then it tries to get the itineraries and put them in the right place and try to separate loads and stores and from and mix and match things. But this is still in SSA form because we haven't done the register allocator yet. And then we get to the register allocator, which has 3 types now. The fast one is like the first one that they've done, and it's just a linear scan, multipass, and just keep going and collecting dead and try to coalesce the ranges later. So it's a really silly but really fast. The greedy is, of course, as the name implies, really slow but actually works well. So it does like calculates the live range, the interference graph, and does some coloring, etc. It's like pretty run-of-the-mill register allocator, and it's the default on all optimized builds, and the fastest default in 0. And the PBQP, which is the partition Boolean quadratic programming, which I don't have a slide because I don't really know how it works, but that was done by ARM, and it's really cool. Arno did this, and it's constraint solver. It was useful for DSP, but then it may be useful for ARM with Neon or something. I don't know why they've done that, but it's pretty cool. And but you can only use this if you specify regalloc equals PBQP, and you're gonna get some surprises, I think. Right, where are we? Oh yeah, the machine function passes. This is something I added later. At this level, you can have special pass, you can register special passes on your target to do pre-register allocator, post-register allocator code gen passes. So, you know, if I think one we have in ARM is load store optimizer and data barrier, redundant elimination. So things that operate on instructions, and either before the register allocator because you don't want to mess up with the register, or after because you have to know which register chain is being used to make sure the pattern matches. So like exception handling tables and prologue and epilogue inserting are all on this frame lowering part as well. So this is all done at the same time as target hooks. And then you get to MC, which is the machine code layer. And that is the part that now decides if you want to output assembly or object files. And of course, the output is different, so don't rely on this output being read back again by Clang and outputted as object codes. It might not be the exact same output as you're getting now, because I don't remember if there's any ASM-specific passes. I think they're all pretty generic, but I don't think we guarantee any kind of consistency between the two. Oh yes, and then so the instruction descriptions are in this table gen description file, and what this does is it goes through this linearized DAG thing to see what do I have in the target description that matches this operation. And because they're already in the target specific description, it should be like a pretty standard pattern matching thing. Sometimes it won't be there. Sometimes you have pseudo instructions, and then you need some C++ code added to the MC layer to lower these things. But most of them will be in the table gen. And then that's the time when it parses the inline assembly, and then starts getting and inserts them into the instruction stream. So at that time, that part is now part of the code. And GCC has these marker flags in the assembly output for whatever was in inline assembly. Yeah, we don't do that, because now it's part of the code. And the register there and using the values that the inline assembly constraints told to use based on the variables. And the MC layer, because it's a library, is also used by the assembler. So either Clang in assembly mode or the LLVM-MC or some others to then assemble or disassemble, because the target descriptions are complete. So you can use them to go from binary to text, from text to binary, and etc. So the assembler, disassembler is just we use this to, so when you have a source code with C and assembly files, you can use Clang on both, and it's Clang in assembler mode. And what it does is uses the table gen and the MC to interpret the assembler, but it also has added things for directives and ABI stuff and sections and stuff, and macros and do we support macros on the assembler already? I think we have some.
The same set, generally the same set that GAS does. Maybe not all of it.
No, yeah. I think a standard macro we do is the other complex macro that.
There are some.
Yeah, yeah. Well, yeah, the disassembler is a bit more complicated, because if you have ARM and thumb code in the same file, you may get a bit trial and error, but it actually works most of the time. And that's our LLVM obj dump and readelf use this to.
Yeah, the interfaces are not the same, so these are not drop-in replacements.
Yes, indeed.
And
Yeah.
their output's not great, has to be said. They're developer tools, they're not.
Exactly, yes. They're still developer tools, even though they have the same name as the GNU tools. They're just developer tools. Again, most of it relies on table gen encodings, but there's a lot of hard-coded stuff, especially in the ASM parser, because we have like ARM, the ISA has been documented, but then ARM CC and GNU has introduced a lot of macros, or not macros, aliases. And so, for instance, if you add with a negative, it may change to a sub. If you use the ADRL, it is actually 2 instructions. So these things have to be hard-coded, and hard-coding different things in the same place doesn't make it pretty. Yeah, the disassembler doesn't know much about the object formats. It's mostly about code. So the object formats have to be, they are encoded into the LLVM obj dump binary itself. So it's part of the main body on how to read these things, and they use the elfcof libraries that LLVM has to read and write. Oh, there you go, table gen. So table gen is kind of, do I have an example? No. So table gen is kind of, it looks like C++ templates with some Lisp syntax. So it's a bit weird DSL, but what it has is, maybe I can click on some of those. That doesn't help. But if I try to, so there you go. This is more or less how it looks like this is defining two patterns from a multi-class RO stuff. And so patterns are you define the patterns, and then you use the def-m is using the multi-class and the pattern to create like an n by m matrix of patterns that would then be used to match. And all of this language is going to be compiled into a table file, and the table file is going to be just plain C++ code. And so that plain C++ code is most of the time is just like a big table, a big array, big matrix, or a big switch, or whenever you say, you know, how do I lower this instruction, then it's just a switch case that goes directly to the right place. So they're horrible things. They take like hundreds of megabytes of data altogether, and this is why we generate them into small files to make the thing readable. And I do this, yeah, and this, there you go. But we use this not just for target description. We use this so the scheduler information is written in this format, the instructions, and even Clang uses table gen for like error messages, warning options. So command line options are all defined in table gen files. Because otherwise you'll be just a big switch in the C file, and that's ugly. So every backend, how you implement a new backend, well, you start by the table gen files, and you start like, you copy from a similar architecture, and you start implementing all the instructions, and describe the pipeline and the scheduler and all the patterns and everything. And after that when you have a simple description, when you start writing the C++ files to use those tables and to then match simple patterns and generate assembly code, and you go from there. So libraries, as I said in the beginning, we have, how much time do we have? A minute. Yeah. Oh, okay, so I won't go into this. Questions?
So you mentioned that the IR is target dependent, but what about instruction set extension? So can I generate, for example, code which uses neon and doesn't use neon from the same IR?
You mean? So in the IR, you can. Because in the IR, that's different than ARM-CC and different than GCC maybe. I don't know. Does GCC have every new instruction is an intrinsic? Or if your RTL has, no, if your Gimbal has like add two vectors, it becomes a VAD. Right, so if you have add with two vectors, it just bails out.
Yeah, if you have a pattern, like intrinsics and MD patterns are different, right? Like if you have an instruction for adding two vectors, yeah, it'll compile, and if you don't have, it'll ice. Like if it needs a certain pattern, right? Compiler needs certain patterns, and if it's not there, it'll actually ice. Yeah, okay. Yeah.
Okay. So the difference in LLVM is that if you have an add in IR, if you have an add with two vectors, that is a vector add. And because adding two vectors is universal across multiple targets, then the targets where the add has a different syntax, different semantics, then they have an intrinsic for it. But all the targets where add is just adding two vectors, then the IR instruction add vector vector is a vector add. So if your backend doesn't have vector adds, then it's going to bail, or what you do is you run a serialization pass before the end to then get all the vector instructions and transform that into the same size divided by the, adding all the lanes together. So in a sense, if you have like add scalar scalar, it's not going to be a vector add. It's always going to be a scalar add. If you have add vector vector and your target has vectors, it will be a vector add. Otherwise, it's going to break because it's going to say, you know what, I don't know what this vector type is. I never heard of it. So in a way, you will have to transform. It looks like it works, but the nuances are that in some, so for instance, the DSP extensions for Neon, like the add, fuse, multiply, saturate, widen, whatever, that's, there are no IR instructions for this because, nobody does that except that one core. So there's an intrinsic for that. And then, of course, if you have the intrinsic, the other target's going to say, oh, I have no idea what that is. Or an ARM without Neon is going to say, I don't know what that is. Right? So you still have to modify the IR for the target that you intend to build to. And so so if you do have vectors, you need vectors in the final. If you don't have, you can transform it, you can pass through opt and say scalarize all vectors, and then you compile to your target, right? That works, but not the same IR. You still have to make it semantically correct for the target that you're trying to build to.
What does the LLVM community consider to be the most important optimization work items at this moment?
I think the basic stuff like inlining, vectorizing, and well, LTO is not an optimization pass, so okay.
They're tuning it for LTO.
Yeah, LTO is just a different. So it depends. For instance, if you go for servers, it is on. If it's for servers, then LTO, PGO are the two big things, but they're not really optimization. Oh, they are like optimization helpers, right? And those are important because for servers, that's what you care, right?
I think it depends on what you mean by the community. I think a lot of the community is made up of hardware manufacturers, and they spend most of their time doing microarchitectural optimizations. So I think most of the effort is on optimization is target specific in the sort of grand scheme of things, as you say, inlining the general stuff. And LTO is the big project that's going on at that part, is my reading of it.
Yeah. And we're doing the thin LTO as well, which is similar to what GCC does for reducing the bloat size when doing LTO. And that is has been driven by the community as well. And I think that's I think it's the same thing as GCC, but specific optimizations are all the same. The ones that are more likely to generate benefits are the big ones. So I don't think there's any special. Yeah, good.
So you mentioned on the slide about the ASM parser that did some simple transformations.
This one?
Yeah. Yeah. Yeah, yeah. So can you give some specific examples about those transformations?
For example, the ADR pseudo instruction would be one of the simple transformations that it might do. As Renato mentioned earlier, changing an add into a sub, it's really because you're going one single pass, there's a very limited amount that you can actually do. It tries to keep what you see is what you get for the main things, but it's not as good as, say, bin utils for doing transformations. So, for example, you might be able to do, because you've not seen all the labels yet, that some things just won't work at all in LLVM-MC that would in bin utils. But yeah, that would be the example.
So one of the things we're doing this year was trying to fudge a few GNU or ARMCC like features, like the ADRL and the load with the electrotransformer load into a move if it's a constant, that kind of thing. And it proved much harder than it should have been, because what it does is, well, the table gen has instructions and pseudo instructions and ASM only pseudo instruction, ASM aliases, right? So the ASM aliases are the one that cannot be generated. Pseudo instructions, and the instructions are the one that get generated by the backend. So the instructions are matched first. And then if it doesn't match anything, it goes to that. And so the alias, which is like ADRL, is the last one to be matched. And you think, okay, that sounds like a good architecture. The problem is that the matching is not precise. So in the load case, it was a load, ARM load with expression, and that was matching a thumb2 load with an immediate. And you say, how does that work? Because this is not thumb, and this is not an immediate, this is an expression that's going to probably become a label. And the immediate handling said, oh, it might be a label, and then we create a label for this and put the expression in there. And then we couldn't do anything, because by the time that it gets to the pseudo, if you create the pseudo, if you create the alias there, it would never be matched, because that would be something completely direct, and you'd already be in the next iteration, and then you didn't see the thing coming. So, and then you have to, make it more specific, or make it into an instruction, and then make sure you never generate this. You see how it starts getting hacky. Actually, Peter's solution was good. It was very simple and to the point, and I think that in the end we did that. The other one that was the problem, the ADRL, is that it's one instruction, but ARM guarantees that it has to be two instructions. So when you say ADRL this, that, it's an add plus add on. So ADRL is like, give me the address of this thing, and it can be anywhere. And because ADR there's a range, right? Because the instruction, the immediate has a limited size, but the ADRL is actually two adds, 32-bit adds. So you can physically get anywhere in your address space. And this is why, and the guarantee there has to be two instructions to make sure to make it easier for the assembler to calculate the size of things. So whenever he sees an ADRL, even if it's early on, it says, okay, that's 8 bytes, right? So, and the problem then is the way we do the transformations, for instance, the load constant to a move, you just say, you get a load, and you say, oh, there's actually a move, and then you return the move, and then it says, okay, this is a different instruction, delete the old one, put the new one in, continue. But the problem with that one, with ADRL, is that it's delete 1, add 2, right? And the whole thing wasn't meant to return 2, right? So then you have to change the whole thing to put in a vector and return the vector, and then other things start failing because they weren't meant to have more than one. And so that's what it means by like a few. There's actually quite a lot of hard-coded transformations, and that's one of the problems. Oh, okay, thank you, everyone.